I apologize for all of the delays in getting this lecture up, but hopefully I have fixed all of my technical difficulties now. So here is your lecture on electric and magnetic forces. And during this lecture, we will be discussing the forces of nature that create electromagnetism and what factors determine the strength of electric and magnetic forces. So first, let's remember where all charges come from. Positive and negative charges always begin within the atom, where you have your positively charged protons trapped in the nucleus of the atom and your negatively charged electrons spinning around in the electron cloud around the nucleus. And if the number of protons and electrons is the same, then we say that the atom has no charge or that it is a neutral atom. But all of those spinning electrons in the electron cloud like to move around. In fact, they jump pretty easily from one atom to another, so atoms tend to gain and lose electrons fairly easily. Whenever an atom gains electrons, it gets negatively charged. Whenever an atom loses electrons, it gets positively charged. And we call charged atoms ions. So if we look at this diagram of an atom, we see that it has lost an electron, it has become a positive ion, and because it is positively charged, it will now attract and bond to any negatively charged atoms that come near it, because opposites attract. So, magnetic and electric forces are natural forces. They occur all around us all the time. Magnetic forces are the attractive and repulsive forces between two poles of any magnet. So, between two north poles, there will be repulsive forces. If we put two south poles near each other, we will see repulsive forces. But if we put a north pole and a south pole anywhere near each other, we will see attractive forces. Electrical forces occur between charged ions, and these are attractive and repulsive forces between charged ions. And we will often see these forces working independently of each other, but we also see them working together. And when you combine electric and magnetic forces, you get the force of electromagnetism. So if we remember that all matter is made up of atoms and that the negatively charged electrons are spinning around every atom, in a lot of substances, in any non-magnetic substance, the electrons are just spinning randomly. And each of these electrons basically has domains that are similar to north and south poles. So as long as the electrons are just spinning randomly and not lining up, then you don't get magnetism. But when the electrons are all spinning in the same direction and all of their north and south domains line up, they create an invisible force known as magnetism. And the power of a magnet, how strong or weak it is known as the magnetic force of that magnet. And the more electrons you have spinning, the more powerful the magnet is. So all magnets have two poles. Every magnet has to have a north and a south pole. You will never have just a north pole or just a south pole. In fact, if you break a magnet in half, you end up with two separate magnets, each having their own north and south pole. So as these poles come close to each other, they will either attract or repel each other. And if we look here, right around the poles of the magnets, we see the magnetic field as shown by the magnetic field lines. Now, of course, normally these magnetic field lines are invisible, but there are things we can do to make them visible. I used iron filings in the classroom to make those field lines visible. So the closer you are to the poles of the magnet, the closer these magnetic field lines are, and the further away you get from the poles, the further apart those magnetic field lines get, and the weaker your magnetic field is. Stronger magnets have larger magnetic fields. So you basically have two different types of magnets. The first kind is a permanent magnet, and a permanent magnet stays magnetic. Over time, there are some things that can happen to even a permanent magnet that can cause the magnetic field to weaken, but for the most part, permanent magnets will keep their magnetic field. So one of the most common examples of permanent magnets are common household refrigerator magnets, like this really super cool Keep Calm and Watch Stranger Things refrigerator magnet. And guys, throughout this video, anytime you see a red arrow, that is one of your Easter eggs. So remember what this magnet says. So not all magnets are permanent magnets, though. You can have a temporary magnet. And I know there's not a specific place in your notes to put this vocabulary term, but I want you to write in your notes somewhere that when electrons are spinning in the same direction, they create domains. And basically this is your north and south poles. So domains occur when electrons line up, and that's what I want you to put somewhere in your notes. There's not a specific line for it, but you will want to have that in there. So in a temporary magnet, the domains only line up temporarily. So, for example, if you take an ordinary iron nail and you touch it to a magnet, the domains in the iron of the nail will temporarily line up and that nail will become magnetized. So you can attach a whole string of paper clips to this new magnetic nail. But if you take the magnet away from the nail, the domains are no longer lined up, the nail is no longer magnetic, and the paper clips would fall. So that is a temporary magnet. And we're going to talk about a different type of temporary magnet a little bit later on. Now, electrical forces are very similar to magnetic forces, and they're related to magnetic forces, but they are created by electric charges. But like magnets, we have two different types of charges. We have positive and negative charges. Also, like magnets, electric forces can either attract or repel. And just like in magnets, like forces repel and opposite forces attract. So when you have a buildup of electrons on an object, like for example, when you rub a balloon on your hair, the electrons go from your hair to the balloon and they build up on the balloon, creating a negative charge. Well, that buildup of charge is called static electricity. That's electricity that's not moving. Remember that static means stationary or still. When electric charges start moving, though, you get electric current. So current is the rate of flow of charged particles. But remember that the only particles that can actually flow are the electrons. So when electrons flow through a circuit, it produces a current which we can then measure in amperes. And once you have current, you can do all kinds of cool things. You can run fans, you can buzz buzzers, you can run alarm clocks, or you can send secret messages from the upside down. So every electric circuit needs to have an energy source, a battery or a cell, that gives energy to the electrons and pushes them through the circuit. And remember that electrons always start to flow out of the negative terminal of the battery, and they are pulled around the circuit by their attraction back into the positive terminal of the battery. Now, anytime you have an electric force, you have an electric field. And electric fields are very, very similar to magnetic fields. And you can have these fields be repulsive or attractive. If you have, for example, two positive charges, you will see that the electric fields are curving away from each other, showing that they are being pushed away. If you have a positive and a negative charge, you will see that the electric field lines are curving towards each other, just like the magnetic field lines curve from North Pole to South Pole. The further away you get from the center of the charge, the further apart the field lines get and the weaker the field becomes. Bigger charges have bigger fields. So not only do electric fields look and act a lot like magnetic fields, electric charges create magnetic fields. So anytime you have an electric current moving through a wire, that wire will be surrounded by a magnetic field. And if you just have a straight wire, that magnetic field is going to be shown in concentric circles around the wire. And this produces an electromagnet. But if you want to produce a really strong electromagnet, you don't want a straight wire. What you want to do is you want to wrap the wire into a coil. And to make your magnet even stronger, you can wrap that coil of wire around a piece of iron or steel. And this will create something called a solenoid. And I know there's not a place in your notes specifically to put this, but somewhere on the outside edges of your notes, I want you to put that wrapping a wire around a piece of iron or steel creates a solenoid. S-O-L-E-N-O-I-D. You're going to want that in your notes for your test this week. So we can increase the strength of any electromagnet by increasing the number of loops in your wire, or by increasing the current or voltage. And you can do that by adding a larger battery, or you can do it by adding more batteries. So we talked earlier about permanent and temporary magnets, and an electromagnet is a temporary magnet. So unlike a permanent magnet, The strength of an electromagnet can easily be changed by changing the amount of electric current flowing through it. Or you can turn an electromagnet off altogether just by stopping the flow of current, by opening a switch, for example. Because you can turn electromagnets off anytime you want, they can be very useful for a lot of different things. For example, scrap yards where you have to pick up heavy piles of metal, or sometimes even have to pick up whole cars and move them from one place to another, use giant electromagnets. So they can turn the electromagnet on, pick up a pile of metal, move it somewhere else, set it down, turn the electromagnet off. Other everyday uses for electromagnets include computer hard drives, stereo speakers, generators, MRIs. If you look at this giant tunnel looking machine that they put you through to take an MRI test, it's actually nothing but a giant electromagnet. Inside of this tunnel is a huge coiled wire, and they're basically sticking you inside an oversized electromagnet. Electromagnets can also be used for toasters. So when you push down the handle of your toaster, it's being held in place by an electromagnet. When your toast is done, the electromagnet turns off, handle pops up, and up pops your toast, or, if you want, a delicious Eggo waffle, just like Eleven likes. That is your lecture on electric and magnetic forces. I will see you in class, everybody. Bye.